Right, okay. In the previous video, we looked at a circuit very much like this one right here, where we have a resistor, a capacitor, and a battery, and we've got a two-way switch. And as we said, we've got a, this capacitor would be charged up by this battery by being in this situation here. So we'd have the positive side there, negative there. And when we eventually switch that to there, what we then observe is the charge moving around this section of the circuit to balance itself out. And it would move around until it was completely discharged. Well, what we would observe in this situation is we'd start off with a voltage that was equal to the potential difference of the battery, because that's the potential difference that was gained across there. So if this was a 6-volt battery, you'd have 6 volts of potential difference across there. And when you switch that to this position, position 2 here, your voltage that you'd read out across this potential voltmeter would be 6 volts. However, that would start to drop because the charge that was stored on here is now being slowly but surely balanced out. And so what's happening, what's going to happen is this charge is going to drop exponentially. And so as a result of that, we need an exponential equation to explain what's going on. So the equation is this: V equals V naught E, because it's an exponential equation, negative T over RC. So let's talk about all of this. This is E to the power of negative T over RC. So this is all to the power of E. We'll talk about rearranging this equation in a short while, but for the moment, let's talk about these terms. So V naught is the V at naught, so the initial voltage, sorry. So that is the initial voltage. And this is the voltage obtained, or the voltage left, after this time. This is the elapsed time. Everything else pretty much stands for itself. So R is the resistance of this resistor, and C is the capacitance of this capacitor. And what's really, really important about this is that this value here has some significance when we start talking about a graphical relationship of V over time. So if I was to draw a sketch of the graph of V against time, we would expect an exponential curve. So we'd start up here and we'd just come down. And obviously it would go on and on and on and on. So the voltage would decay exponentially until it was hardly anything at all. So this is an exponential decay. Now what's really poignant about this mathematically that you need to be well aware of is where this RC comes into account. RC is actually known as something called the time constant. Okay? The time constant, because R times by capacitance, so resistance time capacitance, equals the time constant. And actually you can show that the unit of it is seconds, and I might do that later on in this video if I remember, but I want to get to this point first. So when we times these two values together, we actually get something called the time constant. And the time constant is the time taken for the voltage to drop to 37% of its original value. Okay, so 37%. So you could look at it as the point of view of V naught times by RC. Sorry, not V naught times by RC. V naught times by 0.37 will give you a voltage. And that voltage, V, so this is V naught up here, V will come and give you a value that is otherwise known as the time constant, which also equals to the resistance times the capacitance. Now that's kind of mind-boggling in some respects, but we will be looking to prove that in lesson when we build an RC circuit just like this. So let me make that point again. The time constant is the resistance times the capacitance. Unit is seconds. It is the time taken for V0 to drop to 37%, hence 0.37 has been times by here. And that equals a voltage. And that voltage, when you go across to the line and down, will read off the resistance times the capacitance. Now that is a really profound observation that we can make, and we're going to make that observation in class. So, is it only voltage that does that then? Well, unfortunately no. It also works for two other quantities. It works for current. When I take the current to 0.37 of its original value, so 0.37 IO, go across, go down, that would be RC. What else is it the same for? Charge. Charge is directly proportional to the current, so that shouldn't surprise you too much. The charge be exactly the same. 0.37 of the charge, the original charge, cross, down, RC. Bear in mind, RC is the time taken to go from there to there, okay? Not that that makes a lot of difference at this stage, but when we actually study a nuclear decay, this idea comes up similarly, and you just need to be aware that it's the difference in time from that point to that point. That is even more pertinent if you were given a graph and you were talking about maybe a voltage here, and you wanted to work out the time constant based on this value, for example. Well, you'd have to take it to 0.37 of this value, which may be down here, and go across and down, and it would be the difference between that time and that time. So just be aware that it's the time difference from where that voltage was initially. Remember, that kind of tells itself in the equation what that is, because this is the voltage that you have left after this elapsed time. What's really quite cool about this, where does that 0.37 come from? Well, what's interesting is that you will notice that if you have a time that is equal to RC, then you just have a value, and I'll do this down here, and maybe in a different color actually as well. If you had a time, if the time was equal to RC that had elapsed, well then you'd have 1 over 1, and it'd be minus 1 over 1, which gives you overall minus 1. And if you actually do e to the minus 1 on your calculator, it equals 0.37. So, which quite nicely feeds in to what I've done above here, where I've actually just written 0.37 of the Q, 0.37 of that, because you're just timesing this by 0.37, and that equals V. So this is just this equation rewritten, which is always pretty cool to show. So e to the minus 1 is 0.37. That's where that 0.37 idea comes from. You don't need to know that. That doesn't affect you in any kind of strong way, but I do think it's important to know where that terminology comes from. So that's discharge, and we will be using this to find out unknown values about this circuit. So in this case here, we might be looking to work out what the capacitance is, or we might be looking to work out what the resistance is, and we draw a graph of the voltage over set periods of time. We're going to do this experiment, and we're going to see what the capacitance and resistance is actually equal to the time constant in this case.